So what we're going to look at here is a special type of power series called the Maclaurin expansion. Now this takes the principle of the power series that we've looked at previously and how they are written and comes up with a formula such that we can take any generic function of x and expand it and write it out as a power series. So for example, we could come up with a power series for the exponential function, or for the logarithmic function, or for your sine, your cosine, your tangent function. We're able to take each of these and manipulate it such that using this formula that we're going to look at in a second, we can write it out as a power series. Now Colin Maclaurin, he was a famous mathematician, lived between 1698 and 1746, and he did a lot of work on the power series. This was his main, or one of his main focuses, and he preceded a lot of the work from the English mathematician called Brooke Taylor. Now one of the key things that Colin Maclaurin did was he showed that a lot of power series, under the right circumstances, converge, which is one of the key results that we need and we're going to work with. And he also showed that a series is a function of x within a valid domain of the values of x. So if we set the right conditions on that function relating to the x, we can write the generic function, i.e. maybe our e to the x, as a series of values. Now, the key thing for this is it takes the same general formula every time. The general formula for the Maclaurin series of the function f of x is given by this. So that f of x equals a sum from r equals 0 to infinity of fr of 0, x to the power of r over r factorial. Now this fr to the power of 0 is the rth derivative of the function at the value x equals 0. And this x to the r is x risen to the power that is matching the derivative. So if it's the first derivative, it would be f dash to 0, and this would be x to the 1. It's then over that r factorial. And this can be expanded out and written as f of 0 plus f dashed of 0 x over 1 factorial plus f double dashed of 0 x squared over 2 factorial plus f triple dashed of 0 x cubed over 3 factorial, and it continues on and on like that. Now one thing we've got to think about is, great, it's nice of me to be able to tell you this formula. How can I prove it? Alright, so let's see if we can approach that. Now we know that a generic power series, f of x, as we've covered previously, can be written as a0 plus a1x plus a2x squared, and it can continue on like that. So what we can start to do is look at the format of the Maclaurin series, so the function at the value is 0, and see if we can write it. Now if we imagine we take this initial f of x, and we then set x equal to 0, what that means is that every single term will disappear except from the a0. So we can say that our a0 is the equivalent of f of 0. If we then go back to our original function, the f of x equals a0 plus a1x plus a2x squared and so on, if we take the derivative of that, f dashed of x, what that equals is a1 plus 2a2x plus 3a3x squared, and so on. If we then take the same step as we did in the previous part and set x equal to 0, what's going to happen is everything's going to disappear except the a1. So what that means is that a1 is going to be f dashed of 0. If we then take the derivative yet again, we get f double dashed of x equals 2a2 plus 6a3x, and then it's going to continue on and on again, and again we take that same step and set x equal to 0 yet again. If we set x equal to 0 yet again, everything's going to disappear, but we're going to be left with 2a2 is equal to the second derivative f double dashed of 0. If we rearrange this, what that means is I can write a2 equals f double dashed of 0 over 2. Now, one key thing to remember here. 2 is the equivalent of 2 times 1, which we can write as 2 factorial. So that is the equivalent of f double dash to 0 over 2 factorial. If we then take the derivative a third time, f triple dash of x, what we'll end up getting is everything will disappear except 6a3. Because the next term would be the x, the term after that would then be the x squared, and so on and so forth, so that when we then set x equal to 0 in this case, we'd end up with 6a to 3 equals f triple dashed of 0. And again, I can rearrange this, so I get a3 is equal to the third derivative of 0 over 6. Now 6 can be written as 3 times 2 times 1, which is the equivalent of 3 factorial. So that's the third derivative at 0 over 3 factorial. Now I can continue this on and on and on. We're noticing a pattern here already. Second derivative over 2 factorial, third derivative over 3 factorial. We could continue this on and on and on, and we'd notice the pattern which is up here. And if we take our generic power series, which we had at f of x, and substitute everything in for it, what we then find is that we could write f of x as f of 0 plus f dashed of 0. Now, first derivative, it's just, f dashed to 0 on its own, which is the equivalent of f dashed to 0 over 1, or, if I'm going to write it in the same format I'm doing here, f dashed to 0 over 1 factorial, plus f double dashed of 0 over 2 factorial, plus f, the third derivative of 0 over 3 factorial, and so on. But we have to remember this isn't the whole term. If you look at each of these, this is just the coefficient. So this is at a1, at a0, at a2, at a3, and they're the only parts that will disappear. So we have to keep in the variable. So it's f0 plus f dash 0 over 1 factorial, but I have to keep the x in there. The f double dash to 0 over 2 factorial, I have to keep the x squared in there, because remember, it's just that bit that goes and can be rewritten like this. The third derivative over 3 factorial, that has to be x cubed, and so on and so forth. So there you go. There's the Maclaurin series for a function f of x. That's how we calculate it. We calculate derivatives, set x equal to 0, and we can substitute in there. Now that's the proof of it, but what we need to be able to do is actually use it. So we're going to look at one example here that is a key function that could be quite useful to know. What we want to look at is the Maclaurin expansion for f of x equals e to the x. Now remember what we just said there. F of x equals f of 0 plus f dash to 0x plus f double dash to 0 over 2 factorial x squared, and so on. So what we have to do is take our original function and find the derivatives of it. Well, the good thing is we've got f of x equals e to the x. We know the derivative of e to the x is quite simply e to the x. Then the second derivative again is quite simply e to the x, and so on and so forth. So all of our derivatives are simply going to equal e to the x. If we then substitute in x equal to 0 in all of these, we get f of 0 is equal to e to the 0, anything to the power of 0 is just 1. First derivative at 0, f dash to 0, that's going to be the same thing, e to the 0, which is 1. Second derivative, funnily enough, e to the 0, which is also 1. Beginning to notice the pattern here. Third derivative at 0 is equal to 1. So we know our coefficients, the a0, the a1, the a2, so on and so forth, they're all going to equal 1. So what I'm able to say is therefore e to the x can be written as a power series of the format 1 plus x squared over 2 factorial, which I'm just going to write as over 2, plus x cubed over 3 factorial, which is over 6. Then it'll be plus x to the 4, and that'll be over 4 factorial, which is equal to 24, and so on and so forth. So we'd be able to write the exponential function out in that format. And if you were to take a value of x and plug it into there, and you plugged it into e to the x, you get a value on your calculator. And if you then plug the same value into the x's along here, you'd get an approximation using your series that would get closer and closer and closer to the value of e to the x. So we're able to expand it using that technique. Now this works for most functions. There's very occasionally times where we can't express it explicitly as a power series in terms of x like this, but there's a lot of functions we can do it for. And there's actually a lot of standard functions that it would be very, very useful to know. For example, let's imagine I wanted to find the Maclaurin expansion of f of x equals sine x. I'd follow the same set of steps as I did before. So I'd start with my f of x is equal to sine x. That's my original function there. What I'm then going to do is work it through using the basic technique I talked about before by looking at derivatives. So I'm going to first calculate f dashed of x, or derivative of sine, is cos x. And then I'm going to calculate the second derivative, so f double dashed of x, derivative of cos x, is equal to minus sine x. And I could keep going and going and going. So I could do f to the third derivative of x is equal to minus cos x. Next derivative, the fourth derivative, fiv of x is equal to sine x, and so on and so forth. I could continue to go there. Once I've got all these derivatives, then comes the next important step. For each of the derivatives, what I'm going to do is set x equal to 0. And I do that for every derivative, regardless of how far I could go. I could go up to the 10th derivative if I want. For every single one of them, though, I would substitute in the value of x equal to 0. So if f of x is sine x, for sine x, f of 0 is sine of 0, which is 0. For cos x, x is equal to 0. First derivative, f dashed of 0, is equal to 1. Second derivative, minus sine x, f double dashed of 0. Well, derivative of minus sine x at 0, that's quite simply going to be 0. And then I continue on. So third derivative of minus cos x, f third derivative of 0 is equal to minus 1. And I can keep going. So fourth derivative at 0 for the sine x is back to equaling 0 again. Now, here's something that you have to notice. I've got zeros as some of my answers. So what that's going to mean is if I'm substituting in, so my first term is f of 0, well, my first term, f of 0, is just 0. I'm then going to have my first derivative times x, so I'm then going to have 1 times x. I'm then going to have my second derivative over 2 factorial, so I'm then going to have plus 0 over 2 factorial x squared, and I'm then going to have my next derivative, so I'm going to have plus negative 1 over 3 factorial times x cubed. I'm then going to have my fourth derivative, plus 0 over 4 factorial x to the power of 4, and it would then continue on. Well, again, one thing you need to notice is that if we have our function f of x, so sine x, written as a power series, this first term would disappear. I'd then have 1 times x, so it's going to equal x. The second term would then disappear again because it's got a coefficient of 0. This third term would be minus 1 over 3 factorial, so that would then be minus x cubed over 6. This term would then disappear. I'd then have the next term, which is x to the power of 5. My coefficient for that would actually end up being 1. So I'd end up with plus x to the power of 5 over 5 factorial. 5 factorial is 120. So it'd then be over 120, and then it would continue on and on and on. So sometimes you'll actually end up with a power series where certain terms disappear. Watch out for these because it may ask you for the first 4 non-zero terms. So you'd have to continue on until you get to a point where you've got that many terms that exist and you've got rid of the others. This is working with Maclaurin expansion. We have to make sure we can work this through And remember these steps when it comes to the examples in the exercise video.